Our next speaker is Prabhat Garg. His mentor is Albert Montillo, and the title of his talk is Using Convolution Neural Networks to Automatically Detect Eye Blink Artifacts in MEG Without Resorting to Electrooculography.
Good afternoon, everybody. Where's the... Is it just this?
Yeah, that's it.
Okay. And my name is Prabhat Garg, and we are going to be talking about using deep learning to achieve remarkable performance for artifact detection in MEG. This work has been submitted to MEG 2017, and it's under review. All right, we'll get started. There we go. No disclosures, introduction. Magnetoencephalography, or MEG, is a type of functional neuroimaging tool similar to fMRI or EEG. It detects small magnetic field created by the neurons in our brain. And just like any imaging modality, there are artifacts. Here, the two most prominent ones are eye blink and cardiac artifact. We want to remove these to improve our signal-to-noise ratio. We'll be focusing on the eye blink here. In this graphic, we see that on the left, we have a source-based reconstruction of the brain without the eye blink artifact. On the right, we have with the eye blink artifact, and we can see that the manifestation of the eye blink artifact is diffuse and warrants removal. For our first step is the independent component analysis, or ICA. It's a monolithy data-driven approach that blindly factorizes the MEG data into spatial maps and time courses. We'll be focusing on the spatial maps. Here on the right, we see 20 spatial maps. One of these is going to be corresponding to the eye blink artifact. The problem is that these are ordered randomly and they're not labeled, and we need a human to label them. How do we detect an eye blink? How does a human do it? Well, this one is the eye blink artifact. And you can see this is a top-down view of the scalp, and here's the nose and the ears for orientation purposes. And then we see these ocular regions which have the magnetic signal, the bipolar colors. And you can see the outflux and the influx. Now, hopefully you can tell which ones are which. On the top left, we see that ocular regions have the magnetic signal, and those are the canonical eye blinks. On the right, we don't see that ocular activity. Those are the non-eye blinks. And on the bottom left, these are confounding eye blinks because they don't perfectly match the template up top. And on the right, we have canonical not eye blinks because these are not perfect. These kind of look like eye blinks. So to recap our problems, we are automatically detecting the spatial map of eye blink components from the 20 ICA components. And we will use machine learning, specifically deep learning neural networks. And we'll build a two-category classifier that detects eye blink and non-eye blink, and we'll assign a label to all 20 components. We work with 8-minute resting state MEG from 44 subjects. They're all high school football players, ages 14 to 18, and they're all male. Our pre-processing steps include, first, we downsample our data to 250 hertz. We apply a notch filter to suppress line noise, which is 60 hertz in North America. Then we apply a bandpass filter from 1 hertz to 100 hertz. And to do an overview of our pipeline so far, we have the MEG scan, and on the left, you can see those peaks towards here. These are the eye blink peaks. And then we do the pre-processing, the ICA, then we generate the spatial ICA map. Then we use our deep learning CNN classifier to label it. Then we remove this artifact, and the result is MEG without this artifact, and we still retain all the signal. We'll focus on the deep learning CNN classifier now. What is deep learning? ImageNet challenge was created by Stanford, a group at Stanford that had real-world images, and the task was to label them with an algorithm. Human-level performance is thought to be around 5%, and using traditional machine learning with manual feature engineering, the error was about 25%. In 2012, with CNNs, the error dropped to 15%. In 2015, the error was 3.5%, which is already below 5%, which is the human level. How does CNNs work? Well, we have a 2D image, and there is a sliding window that does matrix multiplications and creates convolutions and creates low-level features. Then we do subsampling or max pooling that keeps the pertinent information and removes the noise, the local noise, and repeat that till we have extracted all the needed features. And to give you an idea of these low-level features, here we see some normal edges, kind of basic edges, and color gradients. These are level 1 features. In layer 2, we can see these are L shapes, they're more complex, and some circles here. If you go even deeper, layer 4, we can see there are some dog faces that are being detected now. So the idea is the deeper you go, the more complex features you can detect. Our network is BlinkNet. Because we had limited data and it was domain-specific data, we could not just use the models from ImageNet. Thus, we had to create our own, and we experimented with hundreds of designs. We did borrow some design elements from the ImageNet models. And we started by 100 image, so it's a 2D image. Those are the dimensions. Then we do 2 convolution steps, the max pooling, the 2 convolution steps, max pooling. And then we do 4 convolution steps, the max pooling, and some fully connected layers. Note that our window size here is 9 by 9. Training versus test. So out of our 44 subjects, 14 were set aside for training and 30 were set aside for testing. So our model learned all the features needed to do the classification using these 14 subjects. And then we tested on 30, and these are the results, 97% sensitivity and 99% specificity. We did the p-value as well, and it was 0.0001. What features are learned? We want to make sure that we can make sense of our model. Here we have an image of cat and dog. It's a real-world image, and if we ask a model, which spatial features in this image are most responsible for correctly classifying a cat, it will highlight the cat area. And if we ask the same question about dog, it will highlight the dog area. And now we do that to our model. We have a non-iBlink and an iBlink, and we ask the model which areas here are most important to correctly classify an iBlink. And then we see that it creates 2 images, one that highlights the ocular regions, one that highlights the central scalp region. Idea being that here we need the signal, the bipolar signal of the outflux and influx in the ocular region, and we don't want any signal in the central scalp region. In conclusion, we created a good model for labeling the spatial maps of iBlink. We visualized the important features learned by our model. And for feature directions, we have been working on this work, and it's currently under review. We are able to detect cardiac artifacts and actually use the time series IC data as well. I'd like to thank the Answer Lab, the Wake Forest people that have been part of the iTackle project. Any questions?
Are there any, there's a question back there.
Yes.
Wait for the microphone. It's on its way. Sonia's running as fast as she can.
So the last step of your BlinkNet is a softmax function, which basically classify it to either iBlink versus non-iBlink. But before that, there's a probability of each of those categories. Have you, I just wonder if there's any correlation with that probability with the amount, the quantity of artifact present in the images.
So our data is skewed. That's your question? Our data is skewed, but we weigh the underweighted class to kind of make up for that.
Specifically, my question is before the softmax output, the last step, there's usually a probability involved in classifying whatever you have into one of those 2 categories.
Correct.
Is there any correlation with that probability with the quantity of artifacts present?
No, we did not see any correlation there.
Okay.
So I have a couple of questions. Did you ever put anybody into the MEG machine and ask them to purposely blink many, many times?
No, we did not.
That might be something interesting to do. And how do you know that the eyes are blinking simultaneously? What if one eye blinks at a time, and wouldn't that generate maybe different independent components that you'd have to take care of?
True, that will create a different type of artifact. We did not look into something like that. We only looked at people blinking at the same time, and but that is a very minority. So that's something we can work on.
So that was a great talk and really interesting. You picked convolutional neural networks.
Yes, sir.
I wonder if that's overkill. In other words, it's real sexy and it's cool and everybody's using it.
Yes.
But if you tried something way simpler, like a support vector machine or so many other possibilities. You mentioned earlier in your talk that CNNs have shown for ImageNet to be superior, and I believe that for dogs and cats, but I wonder whether or not something way less computational intensive might give you numbers that are similar. Did you play around with any other techniques?
We did not, but we did want to play with CNNs, and the project is bigger than just this presentation. But computation time, I'm sure SVMs are going to be much less, but these weren't as bad as we thought they would be.
So my understanding from this is that the blinking is creating an artifact. You're trying to remove that artifact so you can see the original data, right?
Yes, sir.
So how much artifact is that, and how much data variation you're looking at from normal to abnormal? Meaning, is there enough change from normal to abnormal that this noise of artifact is going to overdo or underdo that? You know what I mean? Like, how much artifact are you expecting from blinking?
Almost every person has an iBlink artifact if they're in a MEG machine. And there's a huge difference in subjects or patients' data with artifact and without the artifact. And we can see that when we're processing the data. So this is something that has to be done, but it's so far.
Right. So understand that that's an artifact you want to remove. If that artifact is significant enough, is it much smaller than the difference between normal and abnormal, or is similar? Then it can affect your data, right? From normal to abnormal. Somebody who gets a minor concussion or moderate concussion may have X number of changes. And if this artifact you're removing is going to remove that data out of that. You know,
Yes.
It's the thing we come up with filters, right? You apply a filter to anything, it's going to take away some of your data.
So it's because of the ICA that comes before the CNN classifier. ICA is very good about selecting the individual components. When we remove the iBlink artifact, almost all of the data is retained. It's not like putting an ordinary filter where we're removing a certain wavelength or certain voxels.
Okay. Thank you.
Thank you.
Thank you, sir.